So has anybody heard of Accumulo before just now? A couple people. Well, that's great. So I'm going to move over here. So I'm going to talk about what we were thinking when we designed Accumulo and why it is the way it is. And it's great that we just heard all about Exadata, and actually we've heard a lot of interesting design thinking around how people are building these storage systems and integrating them and why. And so I think this will offer us just another view into that space, but hopefully a slightly different perspective. So when I am talking about design, I'm talking about it in the Steve Jobs sense, which is, why is it the way it is? Another good quote that'll help us out during this talk is that there's no such thing as a free lunch. So there's lots of trade-offs that you have to make. And really, when somebody talks to me about a system, what I want to know is just what are the trade-offs you made and why? Because there's, sometimes either side of a choice is equally good. It just depends on what you care about. So what I really wanted to understand, about like Exadata or any other system that I'm learning about is what do the people who designed it care about, and do I care about those same things? So I'll tell you what the people who designed Accumulo cared about, and then of course it's up to all of us to just figure out where that might fit in our own worlds. So in 2003, at Google, they published a paper about their search architecture. And I don't know, does anyone remember reading this? This is like, and they described the system, and it was like incredibly parallelized. It was distributed, and I believe it was also almost entirely in memory. Does that sound right? Maybe. And what they said was that the thing that they cared about was efficiency, energy efficiency, and price, the price performance ratio. So how much compute do you get for your dollar? There's a lot of things you could care about, I guess, but what Google really cared about was performance per dollar. And that's interesting because right now they're one of the companies that has like gobs of money, and it's interesting for a company like that to care so much about what they spend, but then on the other hand, maybe the reason they have so much money is because they do care about this stuff. So they said that the choice to focus on performance for price pushed them into this space where they decided to use the cheapest hardware they could find and then just make the software deal with it. And this may be like totally old hat to a bunch of you, but I just want to make sure that we're coming at it and we keep this in mind because it's going to drive all the decisions that we make later on. And so they said, this is what the system looks like, and by the way, this is not like a NoSQL database or anything. This is just their indexing system. Different queries go to different machines. The whole index is partitioned. Even a single query can use multiple processors. And it's in the tens of thousands, and the fault tolerance is built into the software. The hardware is pretty bad. It fails all the time, but performance is good because the software can handle it. So they achieved their goal of getting good performance for not a lot of money. And then in 2005, one of the Google engineers, Jeffrey Dean, gave a talk at University of Washington, and this is before they published a paper on a system called BigTable. So he introduced this thing they called BigTable. Who's heard of BigTable? Everybody's heard of BigTable, cool. So very briefly, it's interesting. It's always interesting for me to go back to and see what the world looked like kind of before we knew about all these things. So at that time, not only did they have this success in building out their search engine, but they had a lot of semi-structured data. They had lots of versions of data. They were crawling the web every day or every so often. They had lots of information about their users that they needed to update. And then they had all this kind of weird data they were getting from satellites and geographical data that was a little different than what they had been dealing with before. And then, of course, they had tons of people using the applications that they built all day, every day, hundreds of millions of users. And this is what they said at the time. There's no way we can use a commercial database for this. But they said scale is too much for most commercial databases. And the second thing they said was, even if that's not a problem, even if we admit that there's some databases at scale, the cost would be very high. Now, cost can be measured either in like upfront costs, but there's also a cost of building and owning your own infrastructure. Google chose to build their own infrastructure in the same way they built the web index, right? So they said, we're already invested in this commodity class, cheap hardware. We don't want to have to buy really high-end hardware and have kind of two types of hardware in our infrastructure. And they're focused on what a lot of us have been talking about today, which is there's all these advantages to integrating vertically. They already had a file system called GFS. They had a couple other components that they controlled, and they said, it's okay if we build a new layer on top of these for handling structured data and handling kind of incremental updates and very fast, low latency lookups, because we have these other components that we control. And if we need to make changes to those, we can. And they said, it'd be very difficult, it's easy for us to optimize. It'd be very difficult, though, to have some other system that we don't control sitting underneath a bunch of applications that we're designing, which, by the way, we don't know if they're going to work, because nobody's, built them. At that time, nobody had built the kind of apps Google was wanting to build at the scale they wanted to go to. So they didn't even know what design challenges they were going to have. They just knew if we had a certain level of control over the stack, we're going to be much better off. And also, to Michael's point earlier, they wanted to do it. But then even as late as 2010, another paper came out where they described a system called Percolator, which is, has anyone heard of Percolator? It's much less common. So it's a system for doing multi-row transactions on top of BigTable and incremental updates. They built that because at that time they were actually moving Google's primary web search on top of BigTable. And it was served out of it, at least for a while. I don't know if it still is or not. But that time they said the same thing. They're like, well, we could do this in a database, right? We could try this. But they said, we just don't know how it's going to scale. There's tens of petabytes and thousands of machines. So that was the motivation. That was their motivation. And then when it came to what is this system going to look like, they said, well, we're imagining there's going to be all these processes that are going to be serving user requests, and they're going to need to update just their portion of the world. So for example, I go and I update my user preferences in Google. All it needs to do is just change my settings. It doesn't need to change anything else. They wanted access to the most current data. They need, of course, high read-write rates. They wanted efficient scans, which not all NoSQL databases emphasize. By efficient scans, they mean sometimes I want to just look up one thing, but sometimes I want to look up like 10 or 100 things all at once. And that needs to be fast. And then they wanted to be able to scan over subsets of the data. And this one's interesting. They said efficient joins of large one-to-one and one-to-many data sets. And what they're talking about is not doing joins on the fly. They're talking about pre-joining a bunch of data into a big table. And if there's like a common key, they're just going to store it all together. And then there's also things that they want to look at over time. So that's how they knew they had built the right thing if it delivered those objectives. So that forced them to make the following decisions. It was a highly consistent. They wanted to use consistency. They wanted high consistency over eventual consistency. So how many folks have heard eventual consistency, where it's like, oh, don't use NoSQL because it's eventually consistent. Well, and it's like, well, is eventual consistency even a bad thing, or is it a good thing? But what we've learned, I think, over the years is that eventual consistency is the best you can say about it is it's very difficult to develop applications on systems that are eventually consistent. So if your database is consistent, that makes your life a lot easier. Also, it wasn't designed to span multiple data centers. Now, they've since come out with other things that do that, but BigTable is not one of them. The keys are sorted rather than hashed. So you could, You could build a distributed database by hashing the key, like a set of key value pairs, and then that's how you decide what server they live on. BigTable doesn't do that. It sorts the key space, and then it assigns ranges to servers, which is a lot harder. Also, the servers serving a particular key space, they don't necessarily store the data that they're in charge of. And there's only support for single row transactions. So like I said, later they went on and built something like Percolator for the folks that said they needed multi-row transactions, but those are their designs. Those are their decisions. So that means they decided to build it basically as a big map. So it's key value pairs, but the keys are going to be a little more interesting than just a single value, and we'll get into that. It needs to be fault tolerant, persistent, it's got to scale, and this is what they said back then. It's funny because I think Exadata came out in 2008, and I think at that time, a single, you could correct me if I'm wrong, a single rack could scale to a petabyte. Pretty big, okay. But anyway, it's in the same range. So yeah, and like they said, they were looking at all the commercial database and they're saying, well, we don't, most of them don't scale to this. But this was their target, and then since then they've, of course, gone beyond it. And then perhaps most important, the system had to be self-managing. Because remember, they're building on this super unreliable hardware. It's going to be falling over all the time. And you can't have people running around with their hair on fire in the data center trying to keep stuff running. It's got to be able to handle a huge amount of failure and just keep running with not a lot of humans in the mix. And that's another big difference between BigTable and some other NoSQL databases. Some NoSQL databases make you go find the server that failed, tell its buddies that, hey, this guy's down, because they're still trying to talk to him, and then put another server right back in his place, and even then, they don't quite get it right. So BigTable had to be smarter than that. So I'm going to quickly go through the key value, or through the data model. It starts as a basic key value pair. The keys are sorted, the values are not. The values can be anything, by the way, so you can store like a chunk of a satellite picture in there, or whatever. The key is actually broken up, though, into multiple components. So there's a row ID, a column, and a timestamp. And so you can think of it as like a table, but it's also got this like time dimension. So you can have versions of things over time, which makes sense because they're doing things like crawling the internet every so often. Also notice there's like missing values. So sparse data is not a problem. And the columns can be created dynamically. So if this is a record of the things people have bought, and no one yet has purchased, some sunglasses, then that's okay. The next time you do an insert, a new column would show up called glasses, and it would have the price of whatever that person paid. So it's extremely dynamic. This is what it looks like if you just list the key value pairs. So you got the row ID, the column, the timestamp, and the value. So you can see how you don't pay a penalty for having really sparse or dynamic data. You can just start inserting a whole bunch of stuff, and it's going to store it, and it's going to sort it, and it's going to let you scan over it, and you don't have to supervise it very much. Now, there's a cost to pay for that, which means that your applications have to be able to handle whatever columns come back if you're scanning everything in a row. But BigTable lets you scan just specific rows or specific columns across rows, specific columns within a row. So you won't come across something you're not expecting. But on the other hand, it can be incredibly powerful to be able to scan a row and just say, what do we know? What do we know about this customer? We may know a lot more about Bill than we know about George, but just tell me everything. So that's kind of interesting. The other thing that's interesting about this model is the way you read that table is designed to minimize disk seeks. And again, this was back before kind of Flash came along, where Flash is super good at disk seeks. Spinning disk is, the seek performance of spinning disk was just not improving the way throughput was. So this system, just like GFS underneath it and MapReduce, was designed to take advantage of all the improvements in disk that relate to throughput and avoid seeks at all costs. So at worst, you're going to do a lookup to find the key you want, the first key you want, and you're going to have to do a disk seek to grab a block of those key value pairs off a disk, and then you can bring back just one of those, or you can bring back like 100 of them or whatever. But most user requests in your application are encouraged to be of that design. So try to make it so your table's already organized. The data you need for your user requests can be answered with a single search. What's cool about that is that you get sub-second query latency, no matter how much data you have, without putting all the data in memory. That's still when the data is just sitting on disk, super cold, right? So that's really cool. And that works when you have trillions of key value pairs in a single table. Now, of course, it will also do the typical types of caching. So when you read a block of key value pairs off a disk, you don't just read one, you read like a block of them. And then recently read things can just stay in memory. So if you have temporal or spatial locality hotspots, you can serve that stuff out of memory. So one other thing, the columns actually in BigTable is split into two components. There's a family and a qualifier. The families you have to declare up front, but the qualifiers can be dynamic. It's just whatever you insert into the table. And then you can mark, and the thing about families is you can group them together in locality groups and they're stored together on disk, which means if all you're doing is scanning some of the columns and not all the columns, the database can avoid reading all the columns off a disk across multiple rows. So it can behave like a columnar database if you want it to. Now, if you don't do that, it's going to order things on disk in row order. So it has these properties where it can kind of switch back and forth between a row-oriented versus column-oriented database. And you can mark certain locality groups to be served from memory lazily. The rows can be really, really large. So you could have a single row with 1 million columns or more, which is weird, but it actually comes in handy later. And then, like I said, tables, the rows within a table don't need to have the same set of columns. You pay no penalty for sparseness. And then, so Google had all these components. This is how it worked. BigTable was built on top of GFS, which is a file system, and then a lock service called Chubby. They made it so you could run MapReduce jobs over it, and you could build applications directly on their API. A couple things about how the system actually works. So there's a single master and a bunch of tablet servers. Tables are broken up, partitioned. Well, first, think of a table as a big set of sorted key value pairs. That's partitioned and then assigned. Each partition or tablet is assigned to exactly one tablet server. And that's where you get the consistency. So when you split, though, you always do it on a row boundary. And if you keep inserting data into a tablet, it's going to get big, and at some point, the tablet server is going to split it. It's going to find a good split point, split it, and then the master is going to migrate it. There's an interesting way that BigTable keeps track of all of its tablets and which tablet servers are currently serving them. It uses a hierarchical metadata table to do that. And then when clients need to do a read, they go to, well, here it says Zookeeper, and I've switched the word BigTable for Accumulo, but punchline is Accumulo is based on BigTable. So a client goes to Zookeeper, which is like the lock service, finds the root tablet, reads the metadata table, and then is able to directly read from tablet servers the data it needs. So notice, no data ever goes through the master. And you only go to the Zookeeper if you don't know where any of the other tablet servers live. And clients aggressively cache the metadata table information. Failure, so tablet servers don't have to, so if these little squares that are vertically aligned, that's like a single physical server. Usually each server runs a tablet server process and a data node process, which is just a storage process like GFS or HDFS. Those are typically co-located, but they don't have to be. So notice here we have more tablet servers than we have data nodes. If you lose a physical machine, the data in HDFS or GFS underneath is replicated, so it's okay. The master of BigTable master will automatically reassign the responsibility for the tablets that were on the machine that failed to remaining tablet servers. They read data from the remaining replicas and replay whatever recent mutations were written. And then the storage layer automatically re-replicates stuff underneath. So that's a tremendous advantage when it comes to doing system administration, because you don't have to move data to rebalance the responsibility for serving. BigTable worked out great. Tons of people use it, hundreds of applications. It's still in heavy, heavy use today at Google. The trade-off is people don't really understand intuitively how to create tables necessarily. So it's like, how do I order my data? What do I put in the row ID? What do I put in the column? What do I store as the value? And people are used to general purpose transactions too. But they say the flexibility is worth it. We have a huge amount of control over our stack. Okay, fast forward to 2008, National Security Agency. I was going to ask if anybody here is from the National Security Agency. That'd be funny. So a team of computer science and scientists and mathematicians, myself included, we're looking at all these technologies. We're reading the Google papers. We're looking at Hadoop. By the way, Hadoop is the open source implementation of GFS and MapReduce. We're looking at HBase, which was an attempt to build BigTable. It's an open source implementation of BigTable. And we looked at all this stuff, and we were concerned about storing large amounts of data of different sensitivity levels all in the same place. We looked at all that stuff, and we said, well, we don't think HBase is going to be the right thing for us. We're going to have to build our own, which is a huge undertaking. So we built that, and we extended the design a little bit. We added something called column visibilities to the data model, and there's a back-end processing component called iterators. It was released as an open source project in 2011, and it's still around, it's still out there. The change we made was we added this component to the column called the column visibility, and that lets you control what clearances are required to access that key value pair. So it's extremely fine-grained. And so imagine like that Bill's phone number for some reason is private, but his age is public. You can do things like that. And you don't just have to use simple labels like private, public. You can use complex expressions. So this is what it looks like if you look at all the key value pairs. There's a couple other advantages. Column families don't have to be declared up front. They're also dynamic. So the whole system just ingests whatever you give it. And then there's something else called a batch scanner, which lets you scan in parallel, which is really nice for using secondary indexes to identify records you want and then fetching the records, just like a regular database. So, and this all enabled what we were really after, which I'm coining the archaeologist's approach to data. So imagine you're an archaeologist and you're uncovering bones in the dirt, and for a while you're not sure what's bone and what's dirt, right? So you're very delicately brushing, but you don't want to like go in there with a chisel and say, well, I think it's a femur, so I'm going to chip off everything that doesn't look like a femur, right? That would be a mistake, because you don't know. You don't even know what kind of animal it is. Maybe it's not a femur. So you have to just take the data kind of as it is, which Accumulo can do. Avoid making assumptions, avoid cleaning it up. Just take it in, but make it useful. So what Accumulo does is it sorts it, makes it accessible. You can discover things, and you can run processes like MapReduce or Spark over it to do things like clean it up or summarize it or ask questions or do really advanced analytics. So all these components are now open source. Accumulo sits on top of HDFS and Zookeeper. You can build applications directly on it, and you run MapReduce and Spark jobs. Couple benchmarks, and I don't have a disclaimer for these benchmarks, but they're not my benchmarks. So maybe that's an out, maybe not. I'm pretty sure these are accurately reflecting what they're saying in the paper, though. Anyway, Accumulo can do things like run on 1,000 machines and ingest 100 million entries per second, and then store like all of it in like a 7.5 trillion entry table. Like that's one table. And the access time of querying that table, of doing simple scans on that table, is still sub-second. That's what the ingest scale is like. So as you go from 0 to 1,000, you go from, as you go from 300 to 1,000, you go from about 30 million per second up to 100 million per second inserts. That's one benchmark on AWS. The average scan latency, and this is a little bit weird, they were scanning the data the entire time they were ingesting, and they just divided the number of scans they did by how long it took all the data to return. So an individual scan wasn't sub-millisecond, but overall they were able to answer a huge number of requests in on average less than a millisecond. But if you go and just query an Accumulo table, you'll get the answer back in like tens to hundreds of milliseconds usually. Now the administrative overhead, this is really important. While they were scaling from 300 to 1,000 machines, they experienced anywhere from 4 to 9 to 11 failures, right? Just in the short time they were doing these like benchmarks. But the amount of time they had to stop and restart the benchmark and change something, an administrator had to get involved, was 0 all throughout that. And the way it works is you just run your system for a while, things are falling over left and right, and then about once a week or whatever, you go through, you find all the like dead hard drives and you just yank them out and you replace them. But the system's designed to just keep going, and it can even shrink to a significant, like, you could lose like 30% of your cluster, maybe not all at once, but gradually, and it's going to degrade very gracefully. Another proof point was a graph processing benchmark, 1,200 machines, 4 trillion vertices, 70 trillion edges in that graph. It's about a petabyte on disk. They were doing graph traversals, and they could process about 149 million edges per second. Another one, these guys used some really beefy machines, so they had, I want to say they had like 32 cores per machine, which I guess in my mind is beefy. So I had 216 of those, and they could do 115 million inserts per second on that system. But they were not using the write-ahead log when they did that. And they said, it's okay, because we're going to checkpoint the system after every insert, every batch of inserts or whatever. So Accumulo is so scalable that some Accumulo instances have to span multiple deployments of HDFS. So HDFS will become a bottleneck at some point, even though it's really scalable. And Accumulo has the ability to span multiple HDFS instances to get beyond that. Last few things to say, Accumulo in the enterprise. Okay. You know, that was all kind of coming out of the government, right? A lot of those benchmarks are run by folks in the Intel space. So besides the Intel space, everyone in highly regulated industries finds Accumulo interesting. Usually when people approach us about doing a project, they say, well, we read about Accumulo, we heard it had some really interesting security features. And I think that just means that a lot of people are finding that security is kind of holding them back, and if they could just kind of get that out of the way, then they could do a lot of really interesting stuff. Accumulo is also supported, speaking of that open source discussion that was happening earlier, we are very fortunate because, well, in some ways, because we insisted before we got started that, look, if we're going to build this, we're going to make it open source. And the reason why is we didn't want to put forth all that effort and then have it just die on the vine in a government agency and never see the light of day. And there were no guarantees that the funding or whatever to keep that going would continue, because it is tremendously costly to build software like that. So we said, we'll do it, but it's in our best interest and yours, Uncle Sam, to open source this. It helps with recruiting. It just builds goodwill. Like, people are like, wow, government builds stuff and just gives it to the world? That's awesome. But we were lucky in that the Hadoop vendors were waiting to just take it. So they hired a lot of the committers, and they could keep doing the development in a much broader group of people. So that was very fortunate. Enterprises have so much data that they kind of end up being like intelligence communities in a way, where they're coming across data in the wild, even in their own enterprise, and they don't know what it is, or they don't know when it's going to change, because communication across a large enterprise is really difficult, right? So you might be ingesting a data source, all of a sudden there's 3 new fields. Typically that will break a typical ETL pipeline, but Accumulo, if you set it up and you have it just bringing all the data in as is, can be flexible enough to handle that. And what's interesting is people view Accumulo as a way to bring all the data together physically. And why would you want to do that? Because you might want to run a MapReduce job or join that data or summarize it and analyze it in some way. So you have to bring it together physically first, but then protect it logically. So, and Accumulo is such that if you don't have the access to see something, you won't even know it exists. And we're finding that people like having those guarantees. It makes them feel confident enough to contribute their data to a very large shared system. And of course, it has to scale. It's got to be flexible. And the fine-grained access control just makes it so you can choose how and when and to whom you're going to share your data. Now, this is not, Accumulo is not the only thing that has security, but because it had security built in from the beginning and it has such an emphasis, it really gives people that confidence. One other thing, so Accumulo has good support for secondary indexing, which of course all databases have, and you can run MapReduce on it directly, so you don't have to move the data. It's actually anathema in this architecture to move data around, and it's interesting to hear that there's such a wide spectrum of systems when it comes to that. The challenges, though, are it's still a challenge. Unlike Google, a lot of enterprises don't have experts in distributed file systems. So even though the distributed file system underneath Accumulo is open source, you have anybody that can go fix bugs in it. So that's a little bit of a challenge. That's where commercialization and vendors come in. And then making sure Accumulo is doing the right thing for your enterprise security-wise is a challenge. That's kind of where my company plays. We live right on top of Accumulo, and we provide a little bit of more tools that help people adopt and integrate Accumulo and these other components into their architecture and do something useful without doing a lot of engineering up front. There's a couple of resources for you to look up if you're interested in learning more about Accumulo. There's an O'Reilly book. Check out the website. And that is it. So thank you. Okay. Thanks a lot.